I'm gonna solve it first.
Oh, alright.
3/4 of the UCF
The Latin square root number.
Okay. That is true.
Who wants to cover Latin square?
Latin square.
I can cover Latin square.
Okay.
I do, in fact, know Latin.
How much longer
Okay.
do you know?
John, Billy, are there questions that you guys want covered?
I wanted L.
You want to talk about how to do it?
No, like I wanted.
Oh, you
F,
want him to
Because
tell
I
them.
don't know how to do it.
F, am I getting some love for
John?
F?
I can do G.
Which one's G?
Generating the numbers.
Does anyone want to hear the explanation for G? Okay.
Oh, I didn't know if you were asking like what I want.
No, I want to know what you want. Like, because there's so few people here, rather than
Okay.
doing all the problems, it makes sense to see which problems the 5 of you are curious about.
Right. I'd like to hear F and E.
Okay.
And do
I
you
give
solve?
Do you have the
I can
promise
give
then?
you, yeah, I do. I can give you F, and I can think about E. I'm pretty sure I know how to do E. But, like,
Oh, we need to revert to the physical
physical,
problems.
old-fashioned.
Yeah.
E, definitely. I'd like to know.
Which one?
E. You know how to do
I
E?
think I knew E, yeah.
Okay.
I might need some time to think about it, but
Did anyone actually submit E?
yeah, we had the solution in contest, but like I wasn't part of the group that was doing it.
Oh, okay.
And
So it
then
makes
Josh
sense.
got a C after contest.
Oh, okay. But you know what he did, based like the high level idea?
I think so, yeah.
Okay. And then F, who wants to talk about F?
I think I'm the only one who knows how to do it.
Okay, alright.
Only
Is
one.
this a good
The
list
entire
of
world.
problems to go over?
Seems like it.
Everybody happy with this list? Okay. So in future weeks, David will do this process. Where basically, like I want to assign one person to each review whose job it is to see which problems are worth talking about, and then assign who's going to talk about them. Okay. All right. So we good? Everybody? And then we don't know how to do, what was it, A
We don't know
or
A, we don't know K, although K seems pretty doable. Does anyone?
A or K?
I have not
Okay.
worked on it.
Okay.
And
All right.
also
And
G,
or
I think.
do you guys get B?
Yeah, we got B. I don't know how to do B. Josh got B though.
Okay. All right. All right. Sound good? Okay. So who wants to start? Here, I'll order these. Which one's the easiest, do you guys think?
L probably, or G maybe.
Okay. And then this one next.
That was pretty easy, I'd say.
Okay. And then you can do these in whatever order you want. That sound good?
Okay.
Okay, cool.
No.
The dead marker.
Can I see a problem set? Question mark.
Do you want me to bring
I
my
have
copy?
one, but like,
I think I remember the problem. So, G, generating numbers. We've got T, some number of queries, and each query is of the form X, and X is a number from 1 up to 10 to 9. And we have 2 operations we can perform. Type 1 is increment X, and type 2 is make X some new number Y, such that Y and X are anagrams, and Y has no leading zeros. That
That's right.
okay? Yeah. So this is the problem, and we start with some number Z, because that comes after Y. Starts at 1 always, and we want to output the minimum number of these operations we have to do to get X, Z equal to X. So if you play around with it, you'll look at the samples. So one sample they give, which is very useful, is 21. It's helpful to work through these. So for 21, you can go up to 12, and then you can go right to 21. And there's no better way to do this. So this takes 12 moves. So the general idea is going to be when we have some number, we're going to look at the highest, the leftmost digit. It's going to be some number x. And what we want to do is get a 1 in that spot, get some zeros here. So basically, we want to get that power of 10 in the fewest number of steps, and then we can turn x on over here and swap it into place. And so you gotta be careful about how you do this, and you gotta handle the swap function properly. But you can convince yourself that you don't have to worry too much about how you order your increments, because once you have like some digit on in the front, the number of moves you've made since then is going to be the sum of the digits that are in the number. Those are all your increments. And so if you choose your swaps optimally, then there's no better way to get to like the end goal. Hopefully that makes sense.
So we basically need an algorithm to go from 1 to any power of 10?
Yeah.
Okay, and then from there,
Also, like choosing your swaps is important. Or
Choosing your swap is important for the first swap. No other swap matters, sort of.
okay.
So, and the other thing is, if you have something like 800, since it ends in a 0, or rather, since the whole suffix is zeros, you can't swap into this number. So the best way to do it, since you have to increment to get to 800, the best way to do it is to add 1 to 799 and like get the optimal answer for 799. And that's the case whenever this is all zeros.
so that's like a special case. You do something different if it's like 801 or something like that.
Yeah, if it's 801, then like the normal algorithm works. And the normal algorithm will work for 799 too.
Okay.
So the first thing I did was I built like a DP table, and DP of I stored the best answer to get to 10 to the I minus 1, which makes this kind of like easier to handle. And so then I have a recursive method which has what power of 10 am I on, what is the current unit digit a 1 or a 0, I call that F, and is this my first step, which I call set. So if it's your first time entering this function, then you're gonna use this table. You're gonna like get the power of 10. You're gonna add 1. So now we've got some power of 10, and so now we want to increment the units digit until it's equal to the leftmost digit in the number, unless the number is something like 1, 2, 3, in which case it's best to not do any swaps, since this 1 is already in place. And so this starts off as 1. And I also, this is the thing where only the first swap really matters, and after the first swap you just swap the digit into its correct spot. So if you have something like 514, you're gonna go 1 up to 105. But here, you don't want to swap to 501. You want to swap to 510. And so the way I handle this is I just see what the leftmost one is in my number that exists. And I have a table called done. And before I do anything in this recursive method, I just see if this index is done. And if it is done, then I just call it on like power of 10 divided by 10. And I set, and this goes to 0 and this goes to whatever it was. Yeah, and this solves the problem. Do you
It's
have any
almost like
questions?
a digit descent type of thingy, where like you take care of the most significant digit,
Yeah.
and then you next take care of the next, and your recursive function takes which digit you're on, kind of.
Mm-hmm. And f will only ever be 0 or 1 because if you swapped the, like on, when set comes in as 1 for the first time, when you make that swap, f will be 1 in that units digit, but then when you make another swap, it'll be 0. And after that, it'll always be
So
0.
the units
So
digit
you
you're
can
ever
see.
dealing with is always going to be 1 or 0?
Yeah.
Okay.
And the only time that this, like, that you might want to swap a 1, which is always going to be like the leftmost number, the leftmost number you're going to be considering swapping with the units digit is always going to be a 1 since you turned on a power of 10. But this will only happen if you're at the first spot, because otherwise you just swap the 1 into place or leave it there.
What would you do for like 547? What's the path of?
I'm gonna swap colors. Go over here. So 547. You go 1, 100, 105, 501, 507, or sorry, 504.
So you don't want 510 for that one.
Yeah, it's always.
You only want that one there if it matches exactly.
Yeah.
Got it. Okay.
Because if you swapped it here, you're gonna have to like swap it out later, or do more
Right.
increments.
Okay, I see what you're saying.
Yeah.
Okay. That makes sense.
And then.
So then you get, right, so now you're on the recursive, you get this to 4, so I can swap 4 into its place. And then I just have to increment the 7, okay.
Yeah, and in this part, it's a little sketchy. I didn't like prove that it worked in contest, but I just kind of wrote it out for the first like 5 powers of 10.
You mean the DP part?
Yeah, because you only calculate it for like 10 values. And I noticed a pattern. I was like,
So did you
that
just
makes
hard
sense.
code in all the values for it?
No, I
Or
wrote
you
code to
could?
do it, but
Oh, okay.
but I did like hard code that part.
But you saw a pattern to fill in that DP
Yeah,
one.
I'm pretty sure it was right. Yeah, so AC. Questions? Comments? Concerns? Hello. Okay, I'm gonna sit down then.
This looks like a problem where you could go wrong in a lot of different ways. Like you could try something and get a lot of cases, but then miss just a few cases.
I got pretty lucky. I wrong answered, and then I tried 12 or 21, and I tried 13 instead of 12, and I was like,
Okay, so you found a break case very quickly.
Yeah, it was the first case I tried after I wrong answered.
Okay.
And when you swap the 1, I was marking it as done correctly, but when I got to the units digit, I was doing that before I checked the done table, and then I changed that. And it worked.
We couldn't figure out what we were doing wrong, so we wound up writing a brute forcer that just like tried a bunch of random things and then picked the smallest.
Oh, you just tried like different strategies and just
like,
picked the
because
small.
like it's not obvious how you should permute it.
Yeah.
So we just like randomly permuted a bunch of times because we don't have a permutation.
Because you couldn't do all of them, so you just tried some of them, and then just got the best answer.
Or I mean, I guess we could have done all of them. It just would have been a lot of code.
Right.
You
That's
could
really
do
funny.
the offline 10 of the 9 BFS. in
Bad
English.
idea.
That's your answer. The lookup table.
Alright, so problem L is Latin square. So in this problem, you have some square, n by n, and a complete Latin square looks like this, for example. So you have the numbers 1 through n. In each row, you have every number once. In each column, you have every number once. So that means you can't have the same number twice in any row or column. Yeah, so that's what you're trying to build. And you could probably figure out some pretty easy way to do this. You could just do so obviously that works. And that would be kind of a boring problem, so they decided not to do that. So instead, they give you some Latin square with some things already filled in, and then you have to fill in the rest of them, and you want to do it in this way. They also make some guarantees on the things they fill in, but I don't think those are too important, so I'll just kind of ignore them for now. But basically, so let's say they give you just the ones. So the first thing I tried in contest was I'm like, well maybe some greedy works. So
Do you just have any one solution? You
What?
have to produce any one solution that's valid?
yeah, print any solution
Okay.
like completed with that keeps the things they've already given you.
Yeah.
So well actually let's start with just the twos. So the first thing I thought of was like, the greedy looks promising. So then I'm like, well, if we can, like, we need to put one number in each row, so let's just like put it in the leftmost column in each row, and then hopefully we'll avoid collisions there. So you put a 1 here, that's fine. Then you put a 1 here, so like the leftmost one can. And now here, this is where your third one needs to go, but it's not gonna work. So that's a quick break case for some greedy. You might be able to write some like more complicated greedy, but it's kind of confusing how it would work because like there's a bunch of decisions you have to make and they're not obvious.
Or a
that you have to make
backtracker,
it right
which
away.
I'm guessing would be too slow.
Yeah, so it's 100 by 100.
Yeah.
So
Because
yeah,
like you
probably
could try
not.
the one on the third column, like the third row, the second
Yeah.
one. Right, you know what I mean? Like your first one up top. The second one, instead of trying on the second row, try on the third down.
Here?
Yeah. And
Oh,
then
okay.
then one would work out.
Yeah, then you'd be fine. So,
Oh, yeah.
alright, so a couple observations. So first, you need like the same number of, well, okay, so you need different numbers. Because the numbers they've placed have been like all the same, so they'll place like n2s and then maybe n5s. So, or n, what, n minus k.
Yeah.
So you're going to place n minus k different numbers, which means you need exactly n minus k free spots in every row and every column. So if you don't have that, it's obviously impossible.
Wait, they've placed exactly n minus k in each row in each
They
column?
place k numbers
Okay.
where, yeah, so
In
you're
each
going to
row
place
in
n
each
minus
column?
n minus k.
Or
Yeah,
k?
I think so.
Yeah, oh, okay.
Like they promised the number, yeah, so there aren't any 2 in the same row or column, so yeah. So in each row and each column there are k numbers, and the numbers they print will be like all 2s. So it's not like they place a 1 in one column and then a 2 in another column and a 3 in a third column. Like if they're going to place one number in each column, it's going to be 2 for all 3 columns.
Oh, wow, okay.
Yeah. So you have to place n minus k different numbers, and for each of those numbers, you have to place it once in every row and once in every column. So there need to be the same number, there need to be n minus k spaces on the board left in every row and in every column, otherwise it's not going to be possible. So let's say there are. So if we have like one space left, where we have one space in each row and one space in each column, then we know it's going to be possible. And that's because for each row, there's like exactly one space left in it, so we'll fill all those out. And then we know there are no 2 of those in the same column, so it's pretty easy. So now if we know there are 2 spaces, you have 2 spaces left, where you have one in each row, or like in each row and column, then what you want to do is you want to somehow place points so that you can place them. You want to place one in each column so that after you're done, you have one space left over in each row in each column. And it's pretty obvious that you can do that because now you just have like a superset of choices to make than you did for your previous choice. So you have more choices. So like since you have more choices, like you're going to be able to do it. You're going to be able to place like one set of numbers, and then after you do that, you know what's possible with one. So like it's always solvable. So basically, in this sense, greedy kind of does work. Like once you place some number, if you didn't make it impossible by placing that number, then you haven't made it impossible overall. And like obviously this extrapolates. You can do like some proof for it, but I think that's pretty clear. So how do you do it? So now what we have left is like, all right, we have a bunch of spaces that we can't place stuff on and a bunch of places we can. And we want to find some set of spaces so that no two spaces share a row or a column. So we have a bunch of rows, we have a bunch of columns, and for example, the first row and the first column can both be picked, and the second row and second column, the first row and third column, the third row and first column, and then third and second, third and second. So we have this bipartite graph of all possible matchings, and what we want to figure out is let's pick, like we can guarantee, we've already proven that there is some way to pick three edges where no three edges share a vertex. So we want to find that. And then if you run flow, then you'll get a flow of three. So maybe the flow you get is this edge right here, and then this edge and this edge. So that's one possible way to get a flow of three. So if those are the three edges you got, then you know you just picked this square, and this square. Those are three spaces you can put your ones. So you're going to do that for every number you have left, and then your flow, I don't know, it has some bound, but it winds up being a lot faster because because of the constraints on input, it's really hard to make this not work quickly. So you just run like flow 100 times on 100 or on a 200 node graph with at most 1,000 edges, or 10,000 edges, I guess. That's solution. Any questions? Nope. All right.
So in this one, you don't have to do any checking. Like when I get that solution right there, I don't need to check that the resultant flow will be viable.
Yeah, like I proved earlier, like that, like you can always find a matching. Like one's always going to exist, and if it doesn't exist,
Then they gave you bad input.
if it doesn't exist, you would print no.
Oh, you okay?
But that's a red herring because like it is going to
Okay.
exist.
Because like you could set it up like with your graph, instead of having 1, 1, 1, 1, and 1, 1, 1, you could have like 2, 2, 2, and 2, 2, 2, and see, and you should be able to get 6, right? Because there's like 6 opens. You know what I mean? Like
Yeah.
instead of like trying to fill one number, if you get 2, 2, and 2, and then you should be able to get 6. So like if I fill like the green ones, the resultant graph, you don't need to check that it's still fillable, right? Is what you're saying. Like when you put those green X's in,
Yeah.
like that's just an arbitrary flow matching.
Mhm.
You don't need to check that the resultant graph, whether or not it can be filled in.
Yeah, because after you do it,
Mhm.
every row and every column will
Oh,
have
it's been
one
mixed out
one
exactly
free.
once.
Yeah.
Yeah.
So now you just have the one case, which is
Okay.
doable, and then the thing before this would have the 3 case, which
Okay.
goes to the 2 case.
Gotcha.
So that's how it's gonna work. You could like try and run flow multiple times at once, and I was thinking about that. The issue is if you do that, you don't know which ones to assign to which
match to
number.
what, yeah.
So, yeah.
Yeah. And if you guys like this question, a good question, if you haven't done it, it's on Caddis. It's called Science. I think Science is slightly harder than this one, but it's a very, very, very similar idea.
Oh, I remember Science.
This is 2012, University of Chicago, which is the now NAC. And before, they keep on changing their name. There we go. But yeah, if this is a problem that you haven't done this, do this one first, and then to kind of like solidify the idea, do the science question on Caddis. And I think it's
Pretty sure I
ideal.
have AC on Science.
John, should I do F and then you want to do C and then I can do E? That works, alright. So F is kind of tricky to explain. I tried to explain the solution like my teammates in contest, but it's like very abstract and like hard to draw pictures for. So I'm gonna do the best to explain like where the intuition comes from, but it's not super formal.
Hey, David, I'm gonna go.
Okay.
In the future, I got attendance for this one already. I'll just have you, like last semester, I'll just have you send me attendance.
Okay, sounds good. So in this problem, you just started a new Silicon Valley startup cat book, and all your friends are going to share pictures of cats. So there are a bunch of different species of cats, and every species has a certain popularity. So maybe like some species is really popular, some isn't, and you want to devote your bandwidth accordingly. So you want to give more bandwidth to the more popular species, and if it's twice as popular, it gets twice as much bandwidth. Unfortunately, you have some real-world constraints. So maybe this cat is like cat 1, this is cat 2, this is cat 3. Maybe cat 1 is like super popular, cat 2 is kind of popular, and cat 3 isn't super popular. So that's how much bandwidth you would want to give them. But you have like some real-world constraints, which are the amount of bandwidth you have to give to cat 1 can only be in this range. The amount you can give to cat 2 can only be in this range. And the amount you can give to cat 3 has to be in this range. So now you're kind of in trouble because like you can't do exactly what you wanted to. So you want to adjust the amount you give them in a couple ways. So you want the total bandwidth like among all cats to stay the same. And this is like a difficult constraint to follow. That's what makes the problem hard. And then you also want to minimize the sum over all cats.
You seen the Cats movie, David?
I have not, no. I heard it's really creepy. Have you seen it?
No.
Okay. Of x squared, nope, x minus y over y, where this thing is squared. So x is the amount that you give them, and y is the amount you should give them. So like y would be where this point is, and maybe we give them this much bandwidth. So this distance squared divided by this amount. That's how much error you accrue from this cat.
It's kind of some weird constraint.
That is a very weird constraint. So if the problem were just like you wanted to minimize this, then it would be kind of straightforward because then the penalty for all cats for being wrong for a certain cat is they're like all the same. So that makes the problem a lot easier. But because the penalties are different, it's really, man, what is going on? Because the penalties are all different. Thank you.
Hopefully that one's better.
It's much better. All right. Because the penalties are all different, it's like really hard to predict what you should do ahead of time. All right. So the first thing we're going to do is we're going to move everything into its valid constraints. So we're going to take this cat and we're going to put him here. We'll put this cat here. Put this cat here. So when we do that, we're using way less bandwidth than we own. So that's bad. We want to use more bandwidth. So to do that, we're going to have to give some bandwidth to these two cats because this one can't afford any. So how do we want to do that? Well, it might seem that we want to like move both of these over, but the thing to notice is that if we move this over, we'll initially pay less because it's pretty close to where it should be. And since it's like distance squared, like as you go farther and farther out, you have to pay like a more and more extreme cost. So moving this over just a little bit probably doesn't hurt us that much. And then moving this over a little bit hurts us a lot more because we're like squaring some bigger number. But if these are the same distance apart,
solid.
Yeah, these are very solid. Alright, so let's say these are the same distance from where they should be. We don't necessarily want to stop there because we're dividing this by a bigger constant. So for this one, its error is like not quite as big. So we can like afford for this one to be a little bit more because we're dividing it by a bigger number. So like we can afford slightly more error on its part. Okay, so that's kind of the problem and like how to approach the solution. What are bounds? Pretty big, right? So you have 10 to the 5th cats, and then these numbers don't really matter because you use them as doubles anyway, so relative precision. Okay, so what you notice here is like we're only going to increase cats. Let's do another cat actually. So this is cat 4, and maybe it starts here. This is its valid range, and then we keep it here initially. So since we have to like increase our bandwidth in order to hit the total, we're going to increase our bandwidth here, here, and here, or maybe just to some of them. And we're going to do that until we have the amount of bandwidth we need. So this guy is pretty much free to increase because he has no error and like 0 squared is very small. So at first, if we only need a little bit of bandwidth, we just increase this one. But then we'll get to a point,
So for the top for cat 1,
yeah.
its y is way out there. So might
Y
it
is really big, yeah.
So might it be good to decrease him?
Well, if we
Like, might it
decrease
not
him, we'll
cost
have
a
to
lot?
increase everybody else more.
Oh.
So if we decrease him, not only will we accrue error, but we'll like need more error here too.
Understood.
So yeah, so we only want to move like in the right direction. So we'll move in the right direction for some of these 3, but maybe not all of them. So like we want to move this guy because he's pretty cheap. Like initially, like you're really close to the right answer, so error accrues very, very slowly. But then for this one, it's probably better, and this one's probably the worst. So initially we'd move like a little bit here, but then it would get to a point, maybe like right here, where it's beneficial to start moving this at the same time. So now we're moving both of these. And then maybe like we stop here, and then this guy just stays here. So that's our answer. So you have to print where everyone winds up being, which is a little bit annoying. So what you'll notice here is the amount that we stop at. When we're doing that, we're going to like be getting the same amount of error per unit distance we move for all of the cats that we're moving. Because if we weren't, then we would just move the cheaper one more and the more expensive one less. So when we wind up stopping, we're like everybody that we moved until they hit the same error. Or we moved them bounded by this part. Yeah. I don't know what that means. So since we know that, we can binary search the amount. We can binary search like how much they'll be moving when we stop them. And if we binary search and say, all right, they're moving too much when we stop, that means we'll like gain more than the amount of bandwidth we need. So here we need to gain bandwidth. We might also need to lose bandwidth. So if our binary search value is too big, then we'll get too much bandwidth, or we will lose too much bandwidth. But if our binary search value is too small, then like maybe we say, okay, stop moving when your error is 5, when your error per unit distance is 5. So maybe this guy stops here, this guy stops like right here. And then if you like add up these total bandwidths, we won't reach like the fact that we needed this much, and then we got like some free amount from these two. Yeah.
So error per unit distance at some point is just the value of this function at that point?
Yeah, the value of this function in a certain way.
Okay.
So we can take the derivative of this with respect to y. No, with respect to x. Yeah. And then that will be like 2 over y. Is that right?
It should be 2x minus 2x squared. No, stop.
2x minus y?
Yes.
Alright, there you go. So
Derivatives are hard.
that's the derivative. So the 2 doesn't matter because you're binary searching it, so just it's only twice as big. So as you get farther away, your error gets bigger, or like increase in error per step gets bigger, and then this varies between cats, which makes the problem hard. So you can't really do other stuff.
Probably
Yeah.
we should have an
That's
absolute
kind of the
value
idea.
around that. I guess we're just moving right.
Yeah, you got a special case left. Like it's very. Yeah, and then the fact that you have to extract the answer, not just print what the total error is also even more annoying.
So for the first cat, you have them at like the rightmost point initially, but you would start with them all at their lower bound. Yes
No,
or
no. You start with all the cats closest to their correct answer.
Okay.
Like as close to the correct answer as you can be. Now this guy, you're only going to move people right now. We don't have enough bandwidth, so we only move people right. We only increase the bandwidth we give to people.
Could it
So this guy we can just ignore.
be the case that you need
Bandwidth.
Yeah, like might you want to move him left at some point in the future?
Not in this test case. In another test case, you might need to move everyone left. And if that's the case, you'll move no one right. Because moving people right here will only increase the amount we have to pay. So we want to move people right as little as possible, which means we don't want to move people right too far, because then we'll also have to pay to move this guy left. So we'll like double shoot ourselves in the foot.
But once you assign them their initial positions, which are closest, as close as they can get to their ideal position, you'll see if you're using too much bandwidth then.
Yeah.
And then you move
Then we
them
see if we're
left.
using too much or too little.
And you do the same process to move them left.
To move them, yeah. So to move them left, we would like put them all to our closest position, and we'd see, oh, we're using too much bandwidth, so now we need to move everybody left. So everyone who can't move left, which would be these 2 people, we would just ignore. This guy can move left, and this guy can also move left. So we would consider both of them. And then we would binary search what this value is. From this, we can figure out where each person wants to be. So maybe this person wants to be here, this person wants to be here. But then we'd be like, oh, you can't actually be there, so you're here. You can be there, that's fine. So now we know how much bandwidth we have, and from that we can make our decision of whether or not we need to increase or decrease this binary search value.
So for the binary search,
Yes.
binary search the value. For each guy,
Sarah, yeah.
for each guy we might want to consider, we'll calculate how far away from their position right now that'll occur.
Yeah, exactly.
And then
if that's outside of their range, we move it into their range. We might also need to move it back. We might want to move some guy farther than he's allowed to. Like we might like some guy might
You wanna make
very
sure that-
willing to take an error and then you just like can't give it to him.
right. I think that makes sense.
So yeah, really what it comes down to is you're binary searching this thing which isn't the answer, but from which it's pretty easy to figure out what the answer is.
I like you know you want to do it optimally, so you look at all the derivatives, and if there's a good one, you just take it. It's kind of greedy.
Yeah, yeah.
It's nifty.
It's like spending your money. When you spend your money in the real world, you want the last dollar you spend on every item to give you the same amount of happiness.
You gonna quantify happiness for me, Dave?
I am right there, yeah. So however much money you gain, or however much happiness you gain from spending $1 more on a laptop, that amount of money that you spend on a laptop should be the same amount of money, or that happiness per dollar should be the same that you spend per Chick-fil-A nugget. So that's the
You need a
economics.
pretty cheap laptop to match the.
Well, no, I mean presumably you would much rather have a laptop than like one chicken nugget, right?
Yeah.
No.
Yeah,
Well,
that's a very. You know what?
And I'm kind of surprised you have a laptop, Jackie.
One chicken nugget, yeah, but then 700 chicken nuggets. I don't know.
Yeah, so I mean, if you can either pay $1,000 to get 700 chicken nuggets, or you can pay $1,000 to get a laptop, then
I
Let's think about that.
It's a equal toss-up.
Well,
Yeah. Well, I feel like we should.
I don't know. I feel like chicken nuggets should not cost $1 each. But if they're good chicken nuggets,
I
then,
covered this.
well, if they're massive,
Yeah.
I don't know if
Like
that'll
chicken
work.
tenders.
Still coated up though.
Do chicken tenders make you very happy?
well, they're just bigger than chicken nuggets. They're chicken boneless
Got it.
chicken tenders. Just massive
Boneless.
Boneless. Give me a currency, John. Thank you.
So
Blue.
problem So, problem C is called counting palindromes. We're given n, the number of digits, not the
Number of
upper bound on the
digits.
value of n. I misread that. It's not a digit DP.
Yeah, I should do. Fair enough.
Naturally. We're given a prime p and a value k, and we want to answer number palindromes. Ooh. with n digits such that pal is congruent to k mod p. This is pretty crazy. Sounds pretty weird. Like the first idea you might have is like, say you could answer a range, or like just some block. You can say how many ways can I fill this in for each way I could fill it, what values can I get mod p? So you get some frequency values mod p. And if you could get that information for one range, and if you could merge it with another range, then you might be a step closer to solving this problem. But if you think that divide and conquer is log n, not n log n, then you won't solve this problem in contest. So if you, let's go over the naive. The very naive is the n log n p squared divide and conquer, where we just break it into where we recursively break it into ranges, L and M plus 1 and R, and when we get to L equals R, then we can generate, for each digit we could place here, what values could we get mod p, and then we could combine them by, if you combine two ranges with like a p squared loop where we just take each pair of things and add them together and put that in the new frequency array.
So
Or
that would give you a runtime of log n if like your answer is a power of 2 in length, if n's a power of 2. Then you'd have log
well,
n times p squared. Yeah.
just n log n, because you have to
But
consider.
if n's a power of 2, then you only hit log n unique states.
I don't understand. If
So like each time you divide it into half as many digits, no?
Yeah, but we do have to visit each single cell. At like the base case, we're visiting each cell.
But isn't every cell of size 1 the same?
No, because it's at a different power of 10.
Oh, okay.
We'll get there. There's something to be done with this. So, this is trash. So if we have this left guy and this right guy, and we want to get a new guy, and then we can do this process where we loop over every I and j, we take their sum mod p, and we add to this new thing the product of li and rj. So this will properly merge two arrays, and so you might be thinking we can do better than p squared, and you're right. We can do this with FFT in order p log p. So this is looking more promising. We still have an n in our runtime, but we're gonna get rid of it. I promise. So the next step, I'm gonna erase this now. I mean, that's on camera. You gotta pause it for effect. So now we've got some long block. And suppose this is the middle. We know that we're gonna have pairs of equal digits like this. And what else do we know? I guess we don't know much else than that. So, so here's time for observation. I guess number 2. We'll call this number 1. We've got powers of 10, and part of the difficulty here is that each of these powers of 10 is something different, mod p. But you might have seen Euler's totient theorem, which says that a to the totient of p is congruent to 1 mod p if GCD a and p is 1. Now,
How big can P be?
p is up to 1,000.
It's down to 2.
Yeah, it's down to 2. Yeah, I don't know. I don't know why they put a prime number at the bottom but a composite number at the top. I think that's
Yeah.
pretty silly. But anyway, so with this in mind, how many different values of 10 to the x mod p are there really?
990 something.
For a big prime, but for some prime, we can have 10 to the 0, 10 to the 1, all the way up to 10 to the 5p minus 1.
And then they repeat.
And then they repeat. So, with this in mind, we're going to have some 10 to the I here, and it's going to go out until we get to 10 to the I plus 5p minus 1. And I here might not be 0, but we're guaranteed that we're going to hit every value in the exponent. And so this is going to repeat on out just forever. And these blocks are of size 5p. So for a single block, we could apply this technique and for each cell generate its singular frequency array, and then merge all of those with FFT. And so we can do that in p squared log p. that's pretty cool. That is certainly something. And what we know, since these blocks repeat, is that this, whatever frequency array we get from here, is going to be exactly the same as all of the next blocks. Does that make sense?
But like, are we handling the constraint that your first half has to match the second half?
Not yet.
Okay.
So we know that these blocks, they like represent a valid left half, and if we can merge all of them, we can get the answer for the left half.
Sure.
So we need to take care of the right half. So
Well, but like minus the last little bit.
yeah, there's going to be some chunk over here, which might not be a full block, and you have to handle the front guy carefully because he can't be 0.
Okay.
And in the middle here, if n is odd, then skip over the middle guy when you're considering the two halves and add him in at the end. Okay. So now if we look at this right half, we've got 10 to the I minus 1, 10 to the I minus 2. This goes on out to 10 to the I minus 5p. And so, like, there's nothing important about starting this block at this split point. So we could shift this block back to have its left endpoint start here, and we know we'll have the same sort of deal with this block. But if we had some process that would produce an answer for the left half, and we just ran it on the right half, that doesn't make any sense. Because it's not, like, you couldn't merge them, because you can't really enforce, like, post-process that it's a palindrome. If you just have some frequency array, that'd be weird. But so, we know we want these two guys paired, and we want, like, the next two paired. And what we're really interested in is, you know, like, the exponent pairs, like, the exponent of the right guy in terms of the left guy is like a function of how far away you are from the middle.
The exponent of the right in terms of the left.
Yeah, like this. I think you can say that, like, if you have x as the left exponent, so like here x is I, and you have y, then this is gonna always be or wait, yeah. Like we want to store. We want to factor in, when we calculate what this guy contributes, what his counterpart contributes when reflected over.
Okay. And that's like what index it should be at? Or what index it should add to, I guess?
What do you mean?
Like, are we trying to calculate both halves at the same time, or just one half?
We're going to calculate both halves at the same time. We're like,
I guess, how do we do it? Like, how do we enforce this constraint?
Yeah, so you agree with this block is like homogeneous, and all of these blocks when they repeat are the same?
Yeah.
So this guy and this guy have to match up.
Mm-hmm.
And let's look at, like, this guy. This guy has to match with this guy at the end of this block. I guess it's helpful to draw this guy. I'm just gonna so then if we have this guy down here, we want these two to match up also.
Okay.
And so this guy matches with this guy because this guy matches with this guy. Like their exponents mod 5p are the same.
Oh, the same, yeah.
Because we just traveled like one bucket. If we do that again, we'll get to here. But okay, I've messed that up. What's really important about this is that we also have this. This guy matches with this guy because he also travels one bucket length with that purple line.
Okay.
So with
How
that,
does this help us?
yeah. So how this helps us is like how far you travel. Basically, it tells us that if we calculate this, like if we calculate this whole thing and store it in this bucket, then just like how all these blocks are the same, this whole block will be the same as like these two blocks. So I'm gonna like put numbers in. So we got 10 to the I plus 5p. And he's gonna be paired with 10 to the I of, or 10 to the I minus p minus 1. But this guy is the same as this guy. And this guy is the same as this guy. So if here we store, or we use this value to generate this guy's like single cell frequency array, then it's the same as doing it for these two guys. Mod p.
Because on one end you add a factor of 10, the other end you remove a factor of 10, so you don't really change the factors of 10.
Like
there is no net change in the number of factors of 10?
yeah.
There's like one step, or like one block to the left.
Yeah, and the blocks,
and one block to the right.
and moving a whole block is like doing nothing because the blocks are the same.
Yeah, that makes sense.
Yeah, so what this means is that we can do this for each cell in this block, and now we've encoded the information for, like we've enforced in this block that it matches the other half.
So really you're placing like two numbers at the same time when you place one number and you're like, alright, what does this add to our value mod p?
Yeah.
Okay.
And so now we've got some block, and it tells us that like it correctly counted the number of ways to make this a palindrome. Now we just need to know how to merge like all of these blocks in order good. Any ideas?
Well, so in other words, we're taking some polynomial to some very large power.
Yeah.
So we can do that in n times log n plus log power.
N log n plus log, I'm gonna call it exponent. What's n here?
N is how big the polynomial is, so p in this case.
Okay. Yeah. Yeah, so what we do is we treat this as like just some value x, just and this has a length, call it L. Oh, I used L already. Call it M. And the number of buckets we're going to have is M over 5p. And you gotta like be careful about this because like this length might be divisible by 5p and you don't want to throw him in there.
Because of like the 1 or the 0 in the beginning? Because of the 0 in the beginning?
Yeah. So you gotta like, in this.
Like m minus 1.
Well, no, because.
5p, right?
Yeah, m minus 5p. Because we can only exponentiate, we can only answer it for like a multiple of p in length. Since this original thing is, or a multiple of 5p. Since that's what this size is.
So the exponent we want to take it to is like 4 of m minus 1 over 5p.
Yeah, that should work.
Just walk the rest by hand.
And then add in the middle guy. And we do that like fast expo.
Do you know the FFT single log trick?
Single log.
Like, what's your runtime? Is that your runtime?
My runtime is p. So for the first bucket, I do p log p, or p squared log p log n for, or I guess it's this, which is like for each prime, you do some like fast expo to get the power of 10 log p, and then you merge them all with FFT.
Yeah, like, do you run FFT log times, is what I'm saying?
Yeah.
So, like, that part has 2 log factors? You can make it just 1 log factor.
Wait, well this part's,
Oh wait, what is that part for?
no, this part I run FFT p times. This is for building the first block. The initial block. And you have to run FFT to merge each single cell's frequency array, which with like the next one.
Doesn't each cell's frequency array only have size 10?
Yeah, but it's like you store, it's gonna have like sum of like contents is gonna equal 10,
Yeah.
but it needs to be size p because it's of the value mod p.
Oh.
And then, so that's this, and then I do p log n. So you're telling me I can get rid of one of those log factors?
Well, I mean, I think you can get rid of a factor of p in the beginning, and then the log factor in the end.
Which one?
Well, I think you can make it, I mean, like, obviously I haven't solved the problem, but I think, it's possible to do p times 10.
Oh yeah, I mean the 10's in there, but he's a constant. So.
Log n. I think that's possible. So
So you're telling me you
You're
do
doing-
have order n FFT?
this is order n squared FFT. Oh, right? Because 1 is size p, 1 is size 10.
No.
This polynomial is of size 10, right?
It has 10 terms on.
Is 10 not 0 terms?
Yeah.
So we iterate through each of those, and then iterate through all of the other ones. So this is p times 10.
Much better.
This is the cool trick. Do you want to know that trick?
I do.
So the FFT
The
trick.
people want to know too.
The people. All right, welcome, people. All right, so the trick is what FFT does. Like the reason an FFT is helpful is because it lets us get n different points on a polynomial. Now we have a bunch of points on some polynomial.
N or n plus 1?
I guess n plus 1.
I guess probably you could get as many as you want.
Plus 1. Well, it gives us like the nearest power of 2 above n plus 1. But
Okay.
we only use n plus 1. So if you have a polynomial of this degree, then you can see what the coefficients are of all the terms. So, but doing this normally takes n squared time, because you have to evaluate it at n different points. Each evaluation is order n. But instead, if you use FFT, you can get all of them in n log n with some convenient binding factor stuff. So I'm not going to go over how it works, but that's what it does. Then, if you have a bunch of points, like if you have 2 points, so you know like f of 0 equals 7, f of 1 equals 12, f of 2 equals 3, and then we have like g of 0, g of 1, g of 2. If somehow we have all these, we can figure out 3 points for f of x times g of x really quickly. You can just multiply what these are.
Yeah.
We can get it really quickly. So this conversion is n log n, but the multiplication is only order n.
Because we already know all the points.
Because we have the points, yeah. So what we can do is we can convert it, keep it in this point form, exponentiate it, and stay in the point form. And then at the very end we can return. So since
And so here, if we have some frequency array, the points are like I and j, where j is f of I. Is that such a bad shit.
in your frequency array, well, your frequency array is like the coefficients of the polynomial,
Yeah.
right? I'm talking about like if you graph the polynomial, you'd have like some graph, right?
Mhm.
We'd have to evaluate this graph at a bunch of locations. So it's not gonna, the points aren't going to equal this. The points are very non-intuitive.
Okay. That makes sense.
Yeah. So when we actually do points, we do like complex points because math works so nicely. Yeah. So the reason f of t is n log n is because the conversion part's hard.
Mhm.
But once you're converted, then you can do your fast expo log in the converted form. So you only do f of t twice. You only do the transform part, the Fourier transform part twice. And then the exponentiation you just do while you're in the point land. And then you just convert once back at the end.
That's pretty nifty. Maybe I can,
So you can speed this up. I think. I mean, I haven't
sounds
printed it.
legit.
Because like this part makes sense.
But we,
surely, right?
like, we will have a p, like, this will be in there, it'll just be small. Like,
yeah,
for
like
the
I
initial
got
conversion
rid of
and the-
this because this is smaller than this.
Sometimes.
Yeah, yeah.
That's the thing. There's like 3 special cases. If n is 1, just do it.
Okay.
Just Nike, you know. If p is 2 or 5.
Oh. Yeah, this thing.
Yeah, well, so if this is the case, then like the value of the palindrome mod either of these is just dependent on the last digit, because all the tens and the tens just go away, and you can calculate the number of palindromes of length n, or of length like n minus 2.
In like order 1.
I did in like log n, just like 10 to the n minus 1 over 2.
Oh yeah.
And then you
need
choose
that, yeah.
which digit you put at the end. If you do that carefully,
Wait, do you print your answer under mod of like 10 to the next plus 7 or something?
there's 3 mods in this problem. It's kind of gay.
What?
No offense to gay people.
Wait.
Yeah, well, so you gotta take your.
So there's p. Okay, p is one of them.
Yeah, so
Yeah.
values.
Welcome.
Values mod p. Exponents.
Oh, my p minus 1.
Yeah, mod 5 p. And then answers. Mod 10 and then I plus 7.
Okay.
So make sure you use the right mods.
Alright, makes sense.
Yeah, that's.
Now we just did e left. Alright.
Very sparse problem review.
I know, yeah.
That's a pretty clever trick you got there for that last square problem.
Oh, that trick?
I was totally trying to have a graph that included the digits. Yeah, no.
Yeah, I mean, I mean, first, first you want to make the observation that it's always possible. Once you make that observation, it's kind of
Under the constraints of the problem, it's always possible. Right?
Yeah, or you can figure out if it's not possible in order in order to input it right away. So, and then like after that, you just never make it impossible. Okay, so problem E. Problem E is easy query, where they give you an array and ask you to do some easy queries on it.
Sounds pretty easy. Why are we doing it last?
I know, yeah, exactly. Can you give me some numbers here?
1, 69, 420, 26,444.
It can't all be ascending,
Oh,
then it makes
okay. 37. Now can I give you a big
Yeah,
one?
yeah.
26,444.
26,000. And then 13, I guess. Kind of
Yeah,
classic.
definitely.
And then we'll do another 13.
Less thought.
All right. So your query is going to be of the form. They're going to give you some range in the array. Then you're going to take those numbers and you're going to sort them. I can sort in order n because I'm smart. Very quick. All right, and now we're going to take maybe the second
That's a hot
through
prefix of that sorted array though.
third numbers, for example. And now we're going to calculate 3 values. We're going to calculate the OR of all of the numbers that appear 1 time or more, the OR of all the numbers that appear 2 times or more, and the OR of all the numbers that appear 3 times or more. Then we're going to add those 3 ORs up. When I say OR, I mean bitwise OR.
Are we so we get those bitwise ORs. Are we gonna sum them like
So we're
as a
gonna do
bitwise OR, or are we just gonna sum them with numbers?
No, sum them like just numbers. So 37 or 69 or 420, and then nothing,
And then nothing.
and then nothing, and then we want to add them up. And then we'll get whatever this is.
You can't do that in your head?
Nah, sorry. So, alright, so that's the problem.
Okay.
What is the solution? We're given, I hope it's 10 to the 5th, right? Or is it 2 times 10 to the 5th? Well,
Can you do this with a waveless tree?
what part of it?
Figure out
This whole
what
thing, I don't
number.
think you can do with anything.
Oh,
This
okay.
whole thing is very complicated.
Thank you.
Yeah, alright, so you're given
Like the figure
2
out.
times 10 to the 5th test cases. In each test case, you're given an array of length 2 times 10 to the 5th. In each query, you're given 2 times 10 to the 5th queries.
Are there any guarantees on the sum of the
Yeah,
n
it's
and
small
q?
enough that it's
Okay.
probably. Like 2 times 10 to the 5th. So, who's here? I'm not going to explain Mo's. You know Mo's, right?
No.
Really?
Or I know the idea, I never implemented it.
Oh, okay. Well, should I explain Mo's real quick?
Sure.
Alright. So if you have some array, the classic example for a query on an array that you can use Mo's for is median. Actually, median's a bad example.
Isn't I thought it was like how many numbers in this range appear once?
Yeah, that's a better example. Yeah. There's one other one that's really common. How many unique numbers are there? Is a really common one. And I always thought that Mo's was like the only way to do that, but you can do it with a persistent segment tree. Also, with like an n log n instead of n root n. Okay, so what are we counting? How many numbers appear only once? Exactly once?
I guess.
Okay, so you've got like a bunch of ranges. And what you're going to do is you're going to split your array into blocks. And then you're going to sort all of your queries by the block their left point is in. And then you're going to tie break by which position the right block is in. So here I drew all of these so that they all, except for this one, they all start with their left point in the left block. So now we're going to answer them, first this one, then this one, then this one, then this one. Welcome, Travis.
Welcome to the problem review.
So what we can do is we can maintain 2 pointers, like a left pointer and a right pointer, and we have to be able to move these pointers pretty quickly. So right pointer to here, then our left pointer can stay here. So first we can answer this query, then we can answer this query. Then we'll move our right pointer over here, and our left pointer here. So now we can answer this, and our right pointer here, and then our left pointer here. So we can answer this. So when we process some block, we know that our right pointer moves order n times total per block. Does that make sense? So every time we process a block, our right pointer only goes right.
And when we're at something that is a query, we answer it
Yeah.
regardless of how they're ordered. Like the order takes into account where they are in the block.
So within a block, we're going to sort the queries by their right endpoint.
Okay.
Does that make sense? So first we would do this one, and we would do this, then we would answer this one, and then we'd answer this one.
So what if, like for the for one,
Yeah.
what if its left endpoint was at the beginning?
Yeah, we can do that. So, we move both endpoints a bunch. So like when we get to something that's a right endpoint, we're gonna move the left endpoint to wherever it needs to be. But we know it'll only move square root n steps at most, because we know it's in this block.
Mm-hmm.
So like, let's say we're at 3, right? We move this one over here. Now we know, okay, we have to answer this query, which means our left pointer has to move all the way to the beginning. So we do that. So you have to be able to move the pointers and like extend and de-extend the range.
Okay, and like that
Shrink.
movement is like just walk over the array and update your answer.
Yeah, so we can maintain we can maintain a frequency array, and we can maintain how many values appear exactly once. By like every time we change our frequency array, we just keep track of that. So that's Mose. So the right endpoint moves order n per block, and then the left endpoint moves size of block per query, per query. So if we have really small blocks, the left size will almost never move. If we have really big blocks, then the right size only moves like almost n times. So we want to meet in the middle, so we pick square root n. Pretty nice. Alright. So that's Mose. So we're going to use Mose because we have this like kind of annoying frequency thing, and frequencies are hard to deal with. So we're going to do Mose on the queries. So we're going to like do that sort of thing. So like when we're processing this query, we're going to need to move a right pointer out here and a left pointer here. Now we can answer this query. So now what we have to do is like whatever we do in the future, we have to be able to support adding some number to this like data structure and removing it from this data structure. And every time we do one of those operations, we're going to do it n root n times.
What are the bounds on the values?
10 to the 9. It is, yeah. So you have to either like coordinate compress or coordinate decompress or something.
And you would have to maintain what some compressed value maps to. Because you need the actual value to answer the query.
Yeah. Yeah. So I haven't actually coded this. Josh did that, but I can like tell you how it's done. So the other thing we want to maintain is like, alright, so when we're answering this query, we need to keep our values sorted, right? Or like keep our values sorted. We don't actually keep them sorted, but we're gonna have our values sorted. We want it in some range of the sorted values. We need like which things occur how many times, and then we need to know we need
Which ones occur once, twice, and three times?
once, twice, and
Or
three
is it
times.
at least?
No, it's once, twice, and 3 times in this big range, isn't it? Or no, it's not. How do you keep track of
they give us q of these big ranges?
They give you q pairs of ranges. Like each is like a big range, and then within that big range, take this range of smaller elements once you've sorted it. Well, you can get the big range pretty easily. You can get what this is with a bit. You can do get kth to get this thing, right? A bit with frequency array.
I think you actually want to wave the tree, but okay.
Oh wait, can Wavelet do kth largest thing in a range?
Sure.
Oh neat. Okay, well,
Wave the
that's
tree.
exactly what we're looking for. And then we need to well, we can do with the first segment tree we can do like range or, because these are going to be consecutive values.
For the first, like,
For, like,
how many appear once?
How many appear once? You can do segment tree range or.
Wait. Don't they have to appear exactly once, though?
No, once or more.
Okay.
At least once. Then for things that appear twice,
Did you do range XOR?
oh,
and
oh
or
yeah,
that?
yeah. All right, here's what you do. Sorry. So, so we know. Let's say we have. I'm gonna change this array because it's not really that helpful. Sorry.
That's something.
So if we've got like 1, 1, 2, 2, 3, 3, 4, 5, 5. So let's say our query evaluates to 2 and 5. And then maybe we've got like 6, 7, 7, 7 up there or something. Okay. So let's say this is like our sorted, this is our subarray. I've taken liberty of sorting it. We're just maintaining frequency counts in a bit, so it's not the end of the world. Now what I want to do is I want to say, okay, I'm going to take for all of these things, I know their frequencies won't be affected by this smaller range that I pick. Like I know all of the 3s are going to be in here, all of the 4s, and anything less than 5 and bigger than 2. Like all of them are just going to be in here. So here, I can maintain in my segment tree how many things occur 3 times or more, 2 times or more, and 1 time or more. So for all of these things, I can just like manually, like, I can like in my segment tree just maintain them as I do my mows. So this is just a range or. I don't have to take into account this subrange, except for like the 2s and the 5s. Does that make sense?
Since you know what, like, the LR value range you're looking at is for that query, you're going to maintain that, and like that's what your segment tree is going to calculate based off of?
Yeah, so I've got some big array, and then I'm doing mows. So in my mows, I've got some segment tree that only includes the things in this range. Like this is my mows, right? Because I'm doing, like I've already handled this moving my left and right pointer. So
Now
we're processing this range. So in this range, now I'm looking at this sub array of like, so if we take all these things and we sort them, I want to look at this range of things in this whole like subarray. So if I look at this range of things, that's going to correspond to this thing. Other than these bounding two, these two, their frequencies in this subarray are the same as their frequencies in this array. So for them, I can just handle it with like 1 or 3 segment tree range or calls. And that's log n for each of those. And obviously adding and removing from a segment tree is order log n. So then I have these 2s and these 5s, and you can just walk at most 3 steps and see, okay, is this thing a 2? Is this thing a 2? Is this thing a 2? And now we can count, are there 1, 2, or 3 2s in this range?
Why do you need to handle the endpoints specially?
Because we might have a 2 here, right? So we might have 3 2s in the range,
Oh.
but we don't actually have 3 2s in the subrange we selected.
Right. Makes sense.
So you manually handle the endpoints. So then your runtime is the n root n for mows. Then each of those times you do a segment tree call. and then you also do like a +3 for the endpoint stuff.
And if times
This
3,
equals-
you're doing 3 segment tree calls.
Yeah, times 3. That happens too. Yeah, I think that's it. So your segment tree just needs to store like uncompressed values. Like you have to be careful with that. So this log might be a log of 30. Like this might actually be 32, not 20. Not totally sure. But yeah, so it's the end runtime, which passes in C++.
Not Java.
Josh got something to pass. I don't know if it was this, but this I'm pretty sure is right.
Do you need the moves? I feel like you need the moves.
I think you need those. Like frequency stuff is really hard to do, just in general. Because like you don't know what matters in a subsegment. Because like it might not matter to you, but then when you add this other unrelated subsegment, different stuff matters for you.
Could you replace the segment tree with a bit?
Yeah, so for this get kth, you can do that with a bit. And then Josh wound up getting the most of the segment tree methods to like work in the same way a bit works.
I feel like you could do range or with a bit.
You cannot.
Cannot.
No.
Sad.
In order to do stuff with a bit, you need to be able to do like cumulative sums with it, which means you need to be able to subtract. You can't like undo stuff from range order.
But you could do range XOR.
You can do range XOR with a bit, yeah, because you can subtract from XOR. But you cannot do like range GCD with a bit. You could do range OR with an RMQ, but you can't update RMQs. So, yeah. Yeah, you can like hyper optimize segment trees with like array based stuff in indices access.
Yeah, make your segment trees iterative.
Yeah, I'm pretty sure that's what Josh wound up doing. Like totally iterative and very quick.
Very admirable.
Alright, that's it. Do we want an outro, Travis? Can you give us a good outro?
Make sure to subscribe.
Yeah, tell all of our fans to subscribe.
Please subscribe, or I will be mad again. I miss you.
We miss you too, Travis.
What?
We miss you too.